It has opened new avenues for innovation and efficiency in various industries. These systems can learn from their experiences and adapt to changing environments. This adaptability makes them incredibly valuable in dynamic and unpredictable settings. This opens up exciting possibilities across various fields. From healthcare to logistics, AI is enhancing user experiences and optimizing processes, making our world smarter and more efficient. Imagine training your pet to fetch a ball. You start by throwing the ball, and your pet runs after it. When your pet brings the ball back to you, you reward it with a treat. This treat acts as a positive reinforcement, encouraging your pet to repeat the action. This is similar to how reinforcement learning works in artificial intelligence. In this scenario, your pet is like an agent, learning from its environment. The task of fetching the ball represents the environment in which the agent operates. The action of bringing the ball back is what the agent learns to perform. The reward in this case is the treat you give your pet, reinforcing the desired behavior. Over time, the pet learns to associate the action of fetching with a positive outcome, the treat, and thus repeats this behavior to receive more rewards. This is the essence of reinforcement learning. Another analogy to understand reinforcement learning is navigating a maze. Imagine you're in a maze and your goal is to find the exit. You explore different paths, some of which lead to dead ends while others bring you closer to the exit. Each decision you make provides feedback. Each time you choose a direction, you learn from the outcome, adjusting your strategy accordingly. This trial and error process is fundamental to reinforcement learning. In reinforcement learning, an agent interacts with an environment. This interaction is fundamental to the learning process. Think of the agent as a robot, or any entity capable of performing actions, and the environment as the real world, or a simulation. This environment can be anything from a simple grid to a complex virtual reality. The agent takes actions to achieve a specific goal. These actions are decisions made by the agent based on its observations. These actions change the state of the environment, creating a dynamic interaction. For each action, the environment provides feedback in the form of rewards. This feedback is crucial for the learning process. Positive rewards encourage beneficial actions, guiding the agent towards desirable behaviors, while negative rewards discourage unfavorable ones, helping the agent avoid mistakes. Over time, the agent learns which actions lead to the highest cumulative reward, refining its strategy, meaning the most significant total reward over time. This optimization is key to the agent's success. This learning process resembles how humans learn from their experiences. We adapt based on outcomes, we perform actions, observe the outcomes and learn from them, and adjust our behavior based on the feedback we receive. This continuous loop of action and feedback is essential. We strive to maximize positive outcomes, learning and evolving with each experience. Just as the agent aims to maximize its cumulative reward, constantly improving its performance, reinforcement learning has found applications in various fields, revolutionizing how we solve complex problems. One notable example is AlphaGo, a computer program developed by Google DeepMind. AlphaGo learned to play the board game Go at a superhuman level, defeating world champions. It achieved this through countless hours of self-play and reinforcement learning, mastering the game through trial and error. In robotics, reinforcement learning enables robots to learn complex tasks, like grasping objects and navigating unfamiliar environments. These robots learn from their mistakes, continuously improving their performance over time. This has significant implications for automating tasks in manufacturing, healthcare, and exploration.